Everyone's, you want to try? We'll start with these first three, see if you can finish them up. Yeah, thanks.
I use this.
Yeah.
Do you want the net ion too?
Sure, yeah. The net ionic. Thanks. All right, what do you think of this first one? No opinions? Did anybody have something similar? Yeah. So how did you figure out that the Al2S3 is a solid?
I looked at the solubility rules and said that sulfur is insoluble with aluminum.
Right. Good. And then the net ionic equation. So the chloride and the magnesium are the spectator ions that don't participate here. Okay. All right. Yeah, looks good. Okay, who's up for the next one? Okay, thanks. Okay, thanks. What do you think about this one? Number 2. Does that look like what you've got? Something different? Okay. So how'd you figure the hydroxide as a solid? Right. Hydroxides are usually insoluble. So even if you don't have a table around, you could probably guess that. The other way you might have been able to guess the solid if you didn't want to look at the table is to notice that the other one is a nitrate, and nitrates are always soluble. We always see nitrates being soluble. So of course, there's always the option on these things that there's no reaction, that nothing happens. So it's a good idea to consult the table, but you could, if you wanted to make a good guess, you could probably guess that the hydroxide is the insoluble one. All right. What would be the name of the insoluble product? I'm going to practice that a little bit too. What would you call that insoluble product? Yeah, chromium 2 hydroxide. Don't forget the 2, which we now know is the oxidation state of chromium in that one. All right. Next one. Who's got it? we got this one. All right, thanks.
Just the net.
Do the whole thing, the whole balance equation, and then the net ionic equation.
Oh wait. How do I erase?
You can either do Control Z for undo or E makes an eraser. I think you hit Z, so it went to like a zoom. All right, let's try again.
That should be a.
All right, how about this one? It's good. All right. Again, we can look at the carbonate and take a guess at that one. The carbonates are generally insoluble, and the potassium compounds are always soluble. So that's a good way to look at that. And then for the net ionic, yep, that's good. So what would be the name of this precipitate, this insoluble product? Iron 3 carbonate, because the oxidation state of iron here is +3. You see that? Okay, let's do the last couple. What is this CH3COOH? Have you seen that before? Where'd you see it before?
It's C2H3.
Right. So this is the acid form of. This is another way to write acetic acid, which we sometimes see as HC2H3O2, like that. So that's acetic acid. CH3COOH is a little bit more common way to write it because it reflects the actual organic structure, like what the structure would look like. But we'll get into that at a later time. But anyway, please recognize both of those as ways to write the formula of acetic acid. Okay, who wants to try this one? Does that change your answer, knowing that? No? Nobody wants to give this one a try? Yeah, go for it, Jeff.
Do that in ionic too.
What?
Not ionic.
Is it balanced that way?
I think it is.
Yeah.
Okay.
Yeah.
Oh, sorry. Oh, that's right. Hopefully close. Sorry.
All right, look good? Is what you got? Maybe? Maybe not. So you had to recognize that this was what kind of a reaction? really fits into a couple categories, but what's one of them? Well, now you can see it, right? So you can put it in that category. It's not quite combustion because we're not reacting with oxygen, but related to that, it's gas evolution, right? We are forming carbon dioxide and water, but just like combustion. But because there's no oxygen involved as a reactant, it's not combustion. We can call it gas evolution, we can call it acid base, because the acetic acid is reacting with the sodium carbonate, and that actually forms an intermediate of carbonic acid. Carbonic acid breaks down into carbon dioxide and water. Those are the ultimate products. So as we saw in lab, and kind of that general rule that you came up with when you were looking, kind of doing that challenge for one of the parts, what was the general rule? Well, the general rule is when carbonate, sources of carbonate or hydrogen carbonate react with acids, they form carbon dioxide and water. And that's definitely something to keep in mind. So when you see a reaction like this, you know that that's what is produced. Any questions about that one? Okay. The remaining two are, we've got ones that are very similar to what we saw before. So let's put those down here. That's scandium chloride and sodium sulfide. And what are those going to form? Let's see if we can do this one by name. Aqueous scandium chloride and aqueous sodium sulfide produce what? Let's start with the precipitate. What kind of precipitate is it going to produce? Yeah, scandium sulfide. Right, we know those sulfides are usually insoluble. Scandium is technically in the middle, but I believe it's one that really only ever has a +3 charge. So sometimes you don't see it with the parentheses. I think we could go either way on that. And then the other product would be what? Sodium chloride, right? Is that balanced? How should we balance it? You just want to tell me the numbers? Two, 3, 1, and 6. Does that take care of it? That doesn't seem to be right, right? What's the issue here? What's not balanced?
The formula for Na2, it's Na.
Oh, thanks. Yeah, because I was going to say the sodium's not balanced there. But yes, you're right. That works. Thank you. And so then the net ionic equation, we could write all the ions out, or we could see that scandium and sulfide are involved in the precipitate. So those are going to be the things that are in the net ionic equation. Like that. Okay. And then the last one, got lead nitrate, lead 2 nitrate, and cesium hydroxide. Did I get those right? Yeah. Okay, what's the likely precipitate here? Yeah, probably lead hydroxide. And then that leaves cesium nitrate. Okay, now we have to balance those out. That should do it. And our net ionic equation from that would be lead 2 plus 2 hydroxides. Should both be aqueous, by the way. Now that's lead hydroxides. Solid lead hydroxide. You can do this? Feel good about this? Maybe? Okay. Great. What do you want to do next? Can you turn your labs? Yeah. Everybody needs to have a break to get up.
Just want one file.
Yeah, make 2 piles for the 2 different labs. Thanks. And here I got quizzes to get back to. Here's some pre-labs that have been marked off. And here's quizzes.
Are we gonna go over the practice exam?
The what?
The practice exam.
Here, sorry.
Are we gonna go over the practice exam?
Yeah, we can go back to that. if you want. Yeah.
Is this just one?
I think there might be a couple in there. Limited crystallity, limiting reactant, and density. We did it. And I might have not have grabbed them all. There might still be some in there. Other bag. Yeah. Yeah, you can
Although it's balanced actually.
put it together so I make sure that you All right, if you didn't get a chance to get stuff here, that's fine. We'll have plenty of time today. Grab it when you can. Go ahead. You can. I didn't mean to like stop you. Did you get what you needed? Okay. So a couple things to keep in mind when you're going through some of these practice things. There are practice exams posted on Blackboard as well as what I gave you the other day, but it doesn't quite line up right because in the summer semester we do 2 exams and a final, whereas during the regular semester we do 3 exams and a final. So we're like, where we are now would be halfway between the, like in the middle of the second exam. So make sure when you're looking through some example questions, you also look at exam 2, which will have things like this, which certainly would be on our exam, but not in the first exam during the regular fall or spring semesters. A couple other things, a couple dangers of practice exams. People really, really like practice exams because it seems like an exam. It seems like you're being told what's on the exam. But actually, that's a really bad mindset to have because a practice exam, even if it is actually an old exam, is just a sampling of what was asked that particular year, about these topics. There could be any number of things that are not on those practice exams. So make sure that you use the practice exams or other ones that you find as kind of a test for yourself rather than a study guide. Your study guide should be the 150 or so problems in each chapter that we've done so far, and you should work through all those problems and then use the exams just as kind of a final check to see if you can really do it or not. Your question.
Did you write the previous practice exam that you gave us, or no?
No, I haven't written these, but these questions all kind of come from the same place, so you won't see anything grossly different.
Similar to like your kind of test.
Yeah. Yeah.
All right.
How many questions are going to be used?
I don't know. It'll probably be about, I don't know. We'll see how it goes through, how it goes. But we have 3 hours for the exam, and I usually write it to take something around an hour and a half, so that but you can use the whole 3 hours, but I try to write it to be about an hour and a half, like on average. So some people will be done probably less than an hour, and some people, you're welcome to stay here for the full 3 hours. But it'll probably be something like 20-ish multiple choice questions, and then another 10 or so problems, something around that, right? Or around that range.
It's less than 50.
Probably. All right, so that said, let's look at this one because we haven't worked on this yet since we did it in class. So see if you can assign the oxidation states to each of those elements in each of those compounds. That's exactly you would know. I was just looking around, seeing what these are. Looking down for these. All right, let's look at this first one. How do you do this? What did you do when you looked at this?
Went down the chart that we had earlier.
Went down the chart from earlier, and what did you find is the higher priority?
Nitrogen.
Uh,
I know, sorry.
should be lithium, right? The column 1 are always going to be +1. We can rely on that. And that chart is really just a list of what has the most reliably constant charges. And even if you don't remember the chart, you can probably use your experience to figure this out. Like, oh, I know we always see this column being +1, or I know we always see this one being plus or whatever, or minus. So you can kind of think about it that way. So what do we always see lithium as being as +1, right? So we can be pretty confident here that the oxidation state of lithium is going to be +1. And that means nitrogen has to be what? -3. So we're a little less confident about nitrogen because nitrogen can change. It's often -3 when it's a solitary ion, but it does have other oxidation states that we see it in, like in nitrate or nitrite or those kinds of things. So, so we do that one last. All right, what about N2H4? This is a compound called hydrazine or dinitrogen tetrahydride. What do you think? N is -3. Is that what we see from the list? This one's tricky. This one I won't give you one that's this tricky on the exam because you really need the list for this. Yeah. Yeah. According to the list, the H being +1 comes first, right? Is that right? Yeah. So we're going to call this one H +1, which means nitrogen has to be what? -2. That's kind of a weird one. Yeah.
But since there's like multiples of that, does that not count against the chain?
What do you mean?
Like because there's 3 lithiums in the first one.
Mm-hmm.
That's a +1. Would it be like +3 because there's 3?
The overall charge would be, but the individual oxidation state of each lithium atom is +1. So then together they make an overall charge of +3. So when you're reporting the oxidation number of each element, you report each individual element, not the whole group of that element. But yeah. All right, so what about ASO3? What would you call this one, first of all? There's actually a couple ways you can name this. Do you want to try one of them? Yeah, we could call it arsenic trioxide as a covalent compound, which is reasonable. Arsenic being on the line, you might also consider this to be metal, non-metal. It is actually more covalent, so arsenic trioxide is a little bit better, but I wouldn't ask you to name one that was this ambiguous. But another nice thing about oxidation states is you actually have to be able to do this to name it, right? We talked about oxidation states as something later, but really, we actually need that in a compound like this if we're going to name it like a metal, because we need to know the oxidation state of arsenic. So which of those two has a more reliable oxidation state in terms of what we are certain of? Oxygen. That one's definitely going to be what? -2. So then what does arsenic have to be to balance that out? +6. So if we were to name this like a metal, non-metal compound, we would call it arsenic and then a 6 in parentheses, oxide. And then finally, anybody know the name of this one? Potassium, close. Permanganate, yeah. Potassium permanganate. It's a common oxidizer. It's a really deep purple compound used in a lot of reactions as a reducing agent. I'm sorry, as an oxidizing agent. So, what kind of charges should we be sure of on this one, or at least more sure of? Yeah, potassium is going to be +1. What else? Oxygen is going to be -2. So then that leaves us to calculate the manganese charge. And what have you come up with for that? +7, right? So you can see this is actually why this is such a strong oxidizing agent. It has a very, very high oxidation state for manganese, +7. If you look at where manganese is on the periodic table, that means it's lost 7 electrons, not as an ion, but other things, and the oxygens are kind of taking those more. So it really can't lose any more electrons, and it really wants to get some of those back because that's such a high oxidation state. So it can kind of tear electrons off other stuff, and that's what makes it a good oxidizing agent. It wants to be reduced. It wants to tear those electrons off other things, and that's how it's often used. All right. You can do that? Okay, good. Another one that we should look at from this other second exam. So the second exam also has a bunch of these gas problems. We're going to look into that later. We're not going to do that right now. But let's do a problem like this. So here's a nice chemical equation. This test author was nice in giving you all the formulas, but you should be able to set up that equation on your own with just the names of those compounds. So what volume in milliliters of a 0.1 molar sodium phosphate is required to precipitate all the lead 2 ions from 150 milliliters of 0.25 molar lead nitrate? There's a picture. Think you can do this? Or should we get started together? Well, all right, go ahead and get started. And then if you get stuck, let me know where you get stuck, and we'll see if we can work through it. All right, you got this one? People are up looking around, other people still working. Keep working, keep working. What'd you do first? What? Balance the equation. What'd you come up with? 2, 3, 1, 6. Agreed? Yeah, you got to have the balanced equation because we got to do those mole ratios to figure out how much of one reagent we need to react with the other one. What's next then? We got our balanced equation. What's the next step? Yeah, we got to get moles, right? That's always the key of these equations. We're going to take some quantity like volume or mass, turn it into moles so that we can figure out how much of each reagent we have or need, and then get it back into whatever form the question asks for. So in this case, we're starting with a volume and a concentration, and we want to end with a volume of a particular concentration. So let's do what calculations we can, and we can figure out that 150 milliliters of 0.25 molar lead nitrate is 0.0375 moles. Is that what you got? Yeah. Or did you just do it all together in one big line so you don't have the individual numbers? That's fine. So we can look at how to do that too. So this way, we want to know how much of this is required. Now, when we talk about precipitating all the lead-2 ions, it kind of sounds like it's going to be tricky, like we have to account for the differences in formulas because we start with lead nitrate and then we end up with lead with 3 of them in the phosphate as a precipitate. You don't need to worry about that, and the reason you don't is because the equation is balanced. As long as the equation is balanced, that's all accounted for, and you just need to find out the moles that you need. So if we need 0.375 moles of this, we can set up an equivalence to figure out how many moles of the other we need. And this shows us we have 2 of those for 3 of those. And And that gets us 0.025. All right, so the answer to our question in moles is 0.025. There are 0.0250, I guess it should be. 0.0250 moles of sodium phosphate will precipitate all the lead ions from that much lead nitrate. But we're not asked for moles, we're asked for volume in milliliters, so we have to do one more step. We take that 0.250 moles of sodium phosphate and multiply it by the inverse of the concentration. So we need equivalence between moles and liters. We get that equivalence by looking at the concentration. 0.1 molar tells us that there are 0.100 moles in every 1 liter. Oops. So that tells us we need 2.250 liters of 0.1 molar Na3PO4, which is 250 milliliters. Right? Okay, so let's do the big conversion method of the same thing. I do it this way when I show you because I want you to understand the steps and I want to talk about what's actually happening and why it's important. But when it comes to just solving the problem as quickly as possible, a lot of people like to just set it all up in one big string. And certainly if you're doing this in a research setting where you needed to figure out how much of this thing you needed, you just do it, you know, the whole thing as quickly as possible. So let's do that. We'd start with our 0.150 liters of lead nitrate solution times the concentration. You could start with milliliters and do that conversion too if you want. Hopefully we can all do quick milliliter to liter type conversions at this point. Just move that decimal place 3 numbers over. So the concentration tells us 0.250 moles per liter. Then we do our conversion here. Then back to the concentration of the other one. So something like that. That cancels, those are going to cancel. Moles cancel. And we're left with the liters of the other solution. Yeah.
Wait, why do you start with liters and you don't start with the 0.1 mole of Na3?
You could, it doesn't matter. Because you got to multiply those things together, those two together. So you could start with that and then put in the 0.15 liter next and go from there. Yeah. I guess I usually start with that one because it's the only one that's not a fraction, that doesn't have units on the top and the bottom. So it looks nicer, but it doesn't matter. Any other questions about that? You do ones like that? One key with this, when you look at these different solution ones, it's really easy to try to jump to that M1 V1 equals M2 V2 thing, because that's so handy when it works. But that's really only for dilutions. It's true that you can do that this way if you put in a molar thing too to correct for the mole ratio. But if you just do it as is, M1 V1 M2 V2, it's not going to work in stuff like this. The reason is because there's not a 1-to-1 ratio between the two reactants. So you need to account for the fact that 2 moles of this have to react with 3 moles of this, and you're better off doing it like a regular full equation like that. That other equation works nicely for dilutions. We'll stick with that for now, and we'll use it again later when we get into titrations next week in lab. But for now, don't use it for these types of problems unless you feel like you can do the corrections properly. Okay, what do you want to do next? All right, how about, yeah,
Writing equations.
writing equations? Writing more, okay. Yeah, let's look at those again. So let me see if there's anything like that in this particular exam. If not, we'll just have to come up with some. All right, let's just come up with some. Let's look at some other types of equations that we might not have seen so far, or that we've seen, but that might not be as obvious. So we did a lot of practice earlier with the precipitation ones. And what's a good, what do you use to think about, like, how do you know that those equations are going to be those kinds of equations? What do you look for in an equation to know that I'm going to have to look for, see if there's a precipitate or not? Anybody have a thing that you use when you, like, if you looked at an equation, what do you do to try to figure out the products? Yeah.
It's two ionic compounds that are both equally simultaneous. So probably gonna need precipitation.
Yeah, so if we have two aqueous ionic compounds, so there's like an AB plus CD. I know those aren't actual elements, I'm just proving a point here. So you've got these ionic compounds with a positive, negative ion, and then another positive and another negative ion, and they're both aqueous. Chances are that to solve that problem, you're just going to switch partners, right? So you're going to go AD and CB, and then you're going to look at each of those and see if one of them is maybe not soluble. So that's what we've done most of the time. And when you see that, there's actually a name for this type of a reaction. Anybody know what it is? A what? Close. Double replacement, because they're both being replaced. Double replacement. Another name for it is metathesis. So they're kind of all switching partners. Other kinds of reactions that we're not going to see at this time are what we call combination and decomposition reactions. Combination being two reactants coming together to form one product. Decomposition being one thing breaking apart into multiple things. The reason we're not looking at that now is because those are a little bit harder to predict because they don't have nice rules about how you do it. But another one that we have seen is one like this. What kind of a reaction is that? Yeah, we call this a single replacement. So a single replacement is when you have one thing by itself and then two things together. And then you break one of them off by itself and put the other two things together. When do we see reactions of that type? Or when have we seen reactions of that type? What is usually going on to cause a single replacement reaction like this? What else is going on, or what other category do these usually also fall into?
Redox.
Yeah, redox. These are usually redox reactions. At least, I mean, obviously there's tons of reactions all around, but the ones that we've seen, the ones that we've looked at, these tend to be redox. The reason for that is because if one of those parts is going to end up on its own, and the other one's going to end up in a compound, it has to change something with its electrons in order to be able to do that. Like if we've got zinc metal reacting with hydrochloric acid, aqueous HCl, if that zinc is going to then react with things, it's going to have to not be a neutral element anymore. It's going to have to lose some electrons, do something a little bit different. So, so how do we solve a reaction like this? How do we figure out what's going to happen? Anybody? Strategy? Would you know the product of this reaction if I asked you to write it down? Anybody feel good about what they are? No? Okay. Well, first technique is use your experience. You all did this reaction or one very similar to it last week. So what happened? Anybody remember? What happened when you dropped zinc in an acid? Did anything happen? What? It kind of bubbled. Okay, so that's a good clue. It bubbled. So if it bubbled, what are the bubbles? What here could form a gas to make bubbles? Hydrogen. Chlorine could also be a gas. So we can maybe look at both of those. So let's look at both of the possibilities. If we've figured that this is going to be a single replacement reaction, there's only two ways that can really happen. So let's write down those two ways and talk about which one is better or worse. We'll do two pairs of products. We'll say first, the zinc could go, well, the hydrogen could go on its own. And if hydrogen is on its own, then we know it has to be H2. And the zinc could go then with the chlorine. And what is zinc's charge usually? It's +2, so that means it's got to be 2 chlorines. And the other possibility is that the chlorine goes out on its own. That's Cl2. And the zinc goes with the hydrogen. So which of those is more likely and why?
Hydrogen as a gas.
Why?
Because zinc is a positive, it has a positive charge, and hydrogen usually has a positive charge too. So if they
Yeah.
put together, it would be sense.
So that last part that you said, that hydrogen usually has a positive charge, that's kind of the key here. Because actually hydrogen can have a negative charge. There's such a thing as a hydride ion, which is H-. But it's unusual. And so you can actually make hydrogen compounds with metals. You can make sodium hydride, calcium hydride are common. I don't know about zinc hydride. Probably you can make it somehow. But certainly unlikely, and we don't usually see those. So we're going to guess that this is probably not right. And it's okay to think that way. When you see these reaction problems, remember, these are problems. This is exam problems. This isn't just like something you're supposed to memorize. You're supposed to work through it. So if it looks like there could be multiple possibilities, write down those multiple possibilities, think about them, and then try to make a conclusion as to what seems more reasonable or more likely. And in this case, seeing that hydrogen with the metal is kind of weird. It's not something we're really used to. So, zinc chloride seems much nicer, much more common, and it is, and so you'd be right. So the products here are the top choice there, and we'd have to balance this by putting a 2 in front of the HCl. All right, let's try another one. I'm going to say less about this next one. I want you to just figure out the products. We might have done this one before, but that's okay. what do you think? What are the products? What? I don't know. What do you think? Is there a reaction here? Why not? What? Right. So in this case, you have HCl and acid. I should have put aqueous in both of these. I didn't. So you have hydrochloric acid. You have, what's that, HNO3? Nitric acid. And so if you add two acids together, usually not much going to happen, right? So keep that in mind, that that's always a possibility. That sometimes there isn't a reaction, and that's as important as the others. We have to be able to look at some compounds and decide, you know what, I don't think these things are going to react with each other, just as we would with the others that would react with each other. All right. So I'm trying to think what else would end up in there. I don't think they get a whole lot trickier than that. Let's try one other one.
Is there one that ends up being H2O?
Yeah. I'll put down two more reactions because I just thought of another one too. And we'll look at these two together. All right, see if you can write the products for these two. The top one is a weird way to write that reaction, but let me change the top one a little bit because that wouldn't quite work that way. Let's try that with just acetic acid. Sure, we're so good there, sorry. All right, got some products, maybe? Let's do the bottom one first. What kind of reaction is this? What would you call that? Combustion, right? That's a hydrocarbon reacting with oxygen. It's burning. So what are those products going to be? Right, water and CO2. And then how do you balance it? What kind of numbers did you come up with? You got it.
2, 19, 12, 14.
That looks right. These end up getting a little big because we had to double it because that O2 to get the O2 to balance out. Anybody get something different? Some different numbers? Okay. What about the top one? What's going on here? It's kind of like an acid-base reaction, right? We've got acetic acid, and then we've got this NaH, which we just talked about. That's what reminded me of it. It's a totally reasonable compound. It's a real compound. It's got sodium metal. If you remember the chart of finding oxidation states, the sodium, the metals in that column 1 come before hydrogen. So sodium is going to be +1, which means hydrogen has to be -1. So that's actually called a hydride ion, and it's hydrogen of a -1 ion. When you put these things together, you can see that it's actually no different from any other acid-base or other double replacement reaction. The positives going with the of one is going with the negative of the other. So if the Na goes with the C2H3O2, we get sodium acetate. And what is left over with the other two parts coming together? What? H2, which is hydrogen gas. So we would expect that this forms some hydrogen gas. So here's another interesting question about this particular reaction then. Is it also a redox reaction? It is. How do you know? Yeah. Uh-huh. Right. Yeah. So this is an unusual kind of redox reaction in that hydrogen is both the oxidizing agent and the reducing agent. This hydrogen here, it has a +1 charge, and this hydrogen here has a -1 charge. But this hydrogen over on the right has a 0 oxidation state because it's just elemental hydrogen. So the hydrogen from the acetic acid is reduced, and the hydrogen from the hydride is oxidized.
I have a question about how it ends up being aqueous when it was only like a pure liquid.
Yeah, that's a good point. I guess it wouldn't really be a pure liquid. It would technically, acetic acid would be aqueous to start with. A better reaction would be to just react it with water, because sodium hydride is reactive enough that if you try to put it in a water solution, it'll just react with the water, making hydrogen gas and sodium hydroxide. So it's hard, but I wanted to show that equation, so I'm not sure that would actually work like that, or if it would just react. But I think the acetic acid is a more reactive source of hydrogen, so it should still work even if it's aqueous. Sorry, that's an aside. You're right, it should have been aqueous. Other questions about these reactions? All right, let's take a break and get a snack or something. And then when you come back, go through some of the stuff you've been studying, go through some of your problems, and think about what you want to do for the rest of class to get you ready, whether that's mastering chemistry problems, other stuff from the homework, the practice exam that we started on last time, things that you've been getting stuck on with your studying. This is the time to ask about it. So please think about that, and we'll do that when we get back. Yeah, you can do whatever you want. All right, so what do you got? What are you gonna talk about?
Do like a redox of that, like, actually make like a oxidizing agents.
Yeah. Let's do that. Let me check. I'm not sure if this is right. Because I'm kind of making it up, but for our purposes, I think it's right. It's not balanced, but actually, is it? Yeah, it is, isn't it? Okay, so maybe this is right. So find what is oxidized and what is reduced. What's the oxidizing agent, the reducing agent? Yeah.
We wouldn't be expected to find the products for this equation.
Right. Yeah, you would not be expected to come up with the products. So this is the oxidation of methanol. Methanol is oxidized by potassium permanganate to make formic acid. And I believe the byproducts are manganese 4 oxide, which is manganese dioxide, and potassium hydroxides. So let's find the oxidizing agent. And the reducing agent. And how you know based on the change in oxidation states. You got it? Maybe? All right, well, first, before we answer these questions, what elements are changing their oxidation state here? How'd you figure that out? Manganese? And what else? All right, we'll stick with manganese for now. So to figure this out, we got to go assign oxidation states in all the compounds. So we'll start with potassium permanganate. We just did that one earlier. Potassium's +1, oxygen's -2, which means manganese has to be +7. Right? Everybody got that? Okay. Other easy ones that we can assign, we go over here. We know potassium's got to be +1, hydrogen's +1, oxygen's -2. Here, manganese or oxygen is -2, so what's manganese? +4. So there's our first evidence of redox chemistry, that manganese is changing from +7 to +4. So we can see that. Okay, so the tougher ones, not necessarily tougher, but the ones that are often more difficult are the organic ones, or ones that are covalent compounds, not without metals. So let's look at CH4O. Which oxidation states do we assume in that? Yeah, what do we assume H to be? Right. So we assume H to be +1, and we assume oxygen to be -2 generally. And so what does that make carbon here? -2, right? Got -2, -2, and then 4 pluses. So same thing over here. We've got a plus for hydrogen and a -2 for oxygen. So that's 2 plus and 4 minus. So what does carbon have to be there? 2 plus or +2. So there we see another change. So let's highlight those. The changes are carbon going from -2 to +2, and manganese going from +7 to +4. So this will need this may not be right, or at least it's going to need some balancing, because you have to actually balance the electrons. Like if you lose 4 electrons on one side, or from one thing, you have to gain 4 electrons from the other thing, and that's not happening here. So when you get into the second semester class, you'll see how you have to balance out these types of equations. But for now, we can certainly see the change. So +7 goes to +4, and -2 goes to +2. So which one is being oxidized? Which of those 2 arrows, the black or the green, represents oxidation? The carbon one. Because it is an increase in positive charge. So going from -2 to +2 is a loss of electrons. And that means that the green one must be reduction. Okay, so then what's the oxidizing agent? The one that undergoes oxidation or the one that undergoes reduction? The reduction. It's the one that's taking the electrons away from the other one. And that in this case is what? What? Manganese, or specifically the whole reagent would be potassium permanganate, but it's actually the manganese 7+ that's doing it. I don't care how you want to write it. Yeah, it doesn't matter. And so then the reducing agent is the methanol, or really the carbon. Usually when we talk about an oxidizing agent or reducing agent, we're talking about the whole compound. Usually when we say what is reduced or what is oxidized, we're talking about the element, or the individual atom, or ion.
Did you want us to memorize the table, the oxidation priority?
Yeah, the priorities. Yeah, you should know what order to assign them in, at least roughly. Like I'm not going to give you one like with nitrogen and hydrogen, or sulfur and nitrogen. So something where they're really close. I'll just give you ones that You should have a good feel for that table just from what we've done so far, but yeah, certainly take a look at it. All right, what else do you want to talk about? There's book problems, there's mastering chemistry problems, there's practice exam. Yeah, anyone in particular? What?
No.
You just like pull some up and
Yeah.
do them? Well, were there ones that you had specifically had issues with, or you just want some answers to make it
No,
easier?
just in general.
Okay, let's look at some. Let's look at some.
When you're off this too, I have a question.
Okay.
It was from, I think it was either chapter 2 or 3. It was calculating the ratio of the volume of the nucleus to the volume of the whole atom,
Hmm.
and I could not get the right answer.
Okay. We've done those. Oh, this is a good one because we didn't really talk specifically about titrations, but there's kind of a reason for that actually. So let's look at this. And everybody has different numbers for their mastering chemistry, so they may not be exactly the same as mine. But this idea of titration to the equivalence point, what does that mean? We're going to do it next week in lab, but what does that mean? You know, have you ever done that before? It's a way of measuring concentration of an unknown concentration. But all that it means is you're doing an acid-base reaction until the reaction is complete. So at the equivalence point, you have exactly the correct mole ratio of the two reagents. That's all that's talking about. So really, even though they talk about this as a different kind of problem, this titration problem, it's really just an equation or just a stoichiometry calculating moles and stuff problem. So let me show you how that works. You're just assuming that you have a stoichiometric mixture at the equivalence point. So let me copy the equation here. So at the equivalence point, let's say you started with 1 mole of phosphoric acid. At the equivalence point, you'd have exactly 3 moles of sodium hydroxide. So they'd be exactly at the right ratio. So when a question is asking you about the titration, all it's saying is that you have this stoichiometric mixture at the equivalence point. So you've got 31 milliliters of the unknown concentration, so that's what you're trying to find out. And then you've got 27.53 milliliters of 0.13 molar sodium hydroxide. So you actually go through and do this the same way that as that example problem we just did. You just solve for concentration instead of volume. So let's see what that looks like. So here's our volume. And then we've got the concentration. Oops. 0.130 moles of NaOH per liter. So this cancels liters and gives us moles of sodium hydroxide. So then we want to go from moles of sodium hydroxide to moles of phosphoric acid, and we use the equation for that. So that equivalence is 1 to 3. All right, and that tells us moles of phosphoric acid, but ultimately we want concentration. We want moles per liter. So we're going to just divide that by the volume. So 0.03100 liters of the phosphoric acid solution. So if you look at what we've got here, we canceled moles of sodium hydroxide, and now we have moles of phosphoric acid per liters of phosphoric acid solution. So moles per liter of solution is concentration. So our final answer is going to be in moles per liter, or molarity, whatever that comes out to be. Should we try it, see if it works? Point 0.0385 moles per liter, or molar concentration. Let's try that. Yay. Does it make you feel good when the little green thing comes up? You got it right. Yeah.
Question, why did you do 1 mole over 0.31 liters if you don't know?
It's not 1 mole, it's 1 nothing,
Oh.
because we need to divide the moles by liters to get molarity. So we could just erase that one and then just say like divide by 0.13. I guess it doesn't really make sense to not have it there, but it just means we're dividing by the volume to get from moles to moles per liter. Yeah. So that's something that is definitely good to take away, especially next week. I think we're doing 2 labs, maybe just one, maybe the other one's later, that involve acid-base titrations, and they're not a special separate calculation. There's nothing special about them. They're just an equation, and at the equivalence point, you have the stoichiometric mixture, so you can measure that and find an unknown concentration. So if you treat them that way, and rather than a separate type of problem, you can just do it the same way you've been doing all the other problems. All right. What was your question again?
It was one of them from chapter 2 or 3 about the volume of an atom compared to the volume of, the volume of the nucleus compared to the volume of an atom.
Oh, it's not going to give me a list of them here. Let's see. It doesn't tell me either. Okay. Does anybody have a book?
Yeah, page.
Flip through and see. Oh, there it is. Huh, I got lucky. Okay, never mind. Carbon-12 contains 6 protons and 6 neutrons. The radius of the nucleus is approximately 2.7 femtometers, and the radius of the atom is approximately 70 picometers. Calculate the volume of the nucleus and the volume of the atom. All right. Let's make a little drawing here. So here's our nucleus, which we're going to assume is a sphere. And then here's the rest of the atom, which we're also going to assume is a sphere. Zero. Okay. Now the radius of the nucleus and we want our answer to be in cubic picometers. So the radius of the nucleus is 2.7 femtometers, which is 0.0027 picometers. Because picometers, there's 1,000 femtometers in a picometer. And then the radius of the atom itself is 70 picometers. Okay, so let's find the what? You did this already? Yeah, probably.
Yeah.
Because it was chapter 2, Mastering Chemistry.
I just couldn't get the right answer.
Did you do it right? You remember? Okay, well, let's do it again. Let's find out. So we got to figure out the volume of each of these parts. What's the equation for volume of a sphere? Yeah. So that means here we're going to have the volume of our nucleus is going to be 4/3 times pi times 0.0027 cubed. And then the volume of the atom is going to be 4/3 times pi times 70 picometers cubed. So anybody, I don't think my calculator is fancy enough for this, but maybe. I don't know, somebody else type it out, see what you get. What? Yeah.
For the 0.007, I got 8.244 times -8.
All right, let me write that down. Do it again, 8.244
244 times -8. And the other one is 4.44 times 10 to the 6.
Right, say it again.
1.44 times 10 to the 6.
All right, so 8.24 times 10 to the -8th. And we want only two significant figures here. So the nucleus is 8.2 times 10 to the -8th, comma, 1.4 times 10 to the 6th. Okay. What percentage of the atom's volume is occupied by the nucleus? So to get a percentage for the volume, we should be able to divide these and then convert to a percentage, right? So that would be 8.244 or really we should keep with the two significant figures, so we'll do it that way. It's going to be, oops. -9. -8th divided by 6th would be -14th, and then we move it over, so we get -12th. Is that right?
Yeah.
5.9 times 10 to the -12%. So that works. Oops. What was it? 5 point.
So you recommend converting it first before you do any calculations?
You mean converting to picometers?
Yeah.
Yeah. Yeah, I would, because that's what happens, and this common mistake that comes up all the time, is when you convert to a squared or cubed unit, you have to do it multiple times, right? We talked about that once before. It's worth mentioning again because it is such a common mistake. If you know that 1 inch equals 2.54 centimeters, but you want to know about a cubic inch, that means that you have to multiply that 3 times. So a cubic inch is 2.54, that whole number cubed, whatever that comes out to. So you can do that conversion later. I mean, there's no like math rule that you can't do it later, but to avoid confusion, it's easiest if you convert first and then just do the rest of it all in the same units. So that's why I did it that way. It's also like going from one metric unit to the next, like pico to femto or milli to the normal one, is easy. We're really used to it, moving that decimal place three places, one or the other. When you start talking about like converting cubic picometers from cubic femtometers, then it's 1,000 times 1,000 times 1,000, which is a billion. So then like it's easy to drop a zero somewhere. So we're not used to those numbers as much, so it ends up being another potential source of error. There's no reason you can't do it, but I don't know. I think it's easier if you do it this way. So yeah, thanks for that. You don't have to know the volume of a sphere, any of those kind of, geometrical. But I mean, it's probably a good thing to know in life. I don't know, maybe. But I would give that to you for the exam if you need it. All right, what else do you want to talk about?
Just a quick question. When it comes to like gas evolution reactions, it's possible to get a liquid, a gas, and a solid?
Sure. It's always possible to get anything. It just depends on what's happening in the reaction. Yeah. Trying to think of an example of that.
What, calcium sulfate? It was a solid that I got with a measuring chemistry question.
Calcium sulfate is the solid,
Yeah, I mean, yeah, right.
or that breaks up into something. Okay. Yeah, it's certainly possible.
It was. Yeah, it's number 4.9 in chapter 4. Letter D.
4.9?
Yeah, 4.90, sorry.
Oh, 4.90. Yeah, okay. Thanks.
It was letter D.
Letter D?
D. It's in dog.
D is in dog. This one?
Yeah. Oh, I have something different.
This might be one that everybody gets a different equation for or something like that. Because this would be different.
That's not what I had. It's actually kind of the same. Instead of potassium, it's calcium. And then it'd be CH hydroxide.
You see that? Right. So then you can have. So that changes things because calcium sulfate is insoluble, whereas potassium sulfate would be soluble.
That's all. And I was just wondering. I didn't really think about it too much. That it's actually possible to get a solid.
Sure. So let's see what they say about this one then. Yeah. So here you get aqueous potassium sulfate, but in your example, you'd have solid calcium sulfate. Right.
Wait, what's the gas after H2O?
Ammonia. So when you have ammonium reacting with a base, you make ammonia gas.
So is there like a list of gases that we should know for these kind of equations that can possibly come out? So
Um,
we have carbon dioxide.
I would say carbon dioxide.
SO2.
and SO2 are the main ones that I think you should know. I don't care if you know the ammonia one or not. Yeah. I probably won't do that one. Yeah. So what else we got? Some oxidation states, we can do that. We did that today.
Are you gonna ask us about electrolytes? And which one make a strong one, which one make a weak one?
Yeah, let's talk about that for a second. I was trying to look if there was one in here. But it's just another way of asking about solubility, right? So they, I guess, we can just put this definition down. A strong electrolyte is any ionic compound that's soluble or strongly soluble. So all of the things that follow the solubility rules, those solubility rules, by the way, only apply to ionic compounds. Those are only for ionic compounds. So you've got, sodium chloride and calcium nitrate, whatever else. Those would all be strong electrolytes. They're soluble, which means they totally break into ions in solution and make for a strong electrolyte. It means electricity can pass easily through there. Yeah.
Are the strong acids also?
The strong acids are also strong electrolytes, yeah. So then you've got non-electrolytes. Which are mostly the covalent soluble things, like sugar is always kind of the classic example. You dissolve sugar in water, it's highly soluble, but it doesn't break up into any ions. You don't end up forming H plus or anything like that. It just stays a whole sugar molecule. So it's not an electrolyte because it doesn't make ions in solution. And then in the middle, you have the weak electrolytes, which are things like the weak acids and bases, which are any acids besides kind of the big ones that we see all the time, like hydrochloric acid, sulfuric acid, nitric acid. Those are all strong acids. Weak ones are things like acetic acid or other organic acids, benzoic acid, things like that.
Are strong bases then? Strong electrolytes or no?
Strong bases are strong electrolytes, yeah. Strong bases also kind of fit into this because they're things like potassium hydroxide, kind of like the hydroxides that are highly soluble, or the hydroxides that are soluble.
How do you determine which ones are strong?
With solubility rules.
Oh,
For bases, you mean?
yeah.
Yeah, with solubility rules. So the strong ones will be things like potassium hydroxide, any hydroxides that are soluble. And then the hydroxides that aren't soluble are not electrolytes, and the hydroxides that are kind of soluble are the weak ones based on the table. Other bases, non-hydroxide bases like ammonia, are also in the weak category.
Is it when it's sometimes soluble, sometimes not? Is that what it's like?
No, when it says slightly soluble. So there's a few things on the chart that says slightly soluble when with whatever. That would be an example of a weak electrolyte. Yeah, good question.
What if you got two things that fit in the same category? How would you figure out which one's more conductive?
You have to measure it. You have to do the experiment. there's not really a way to tell. You can look up the solubility. You can look up the ions formed in the solubility. It's called the solubility constant. We'll do that next semester, and you can find how many ions of this are formed in solution versus this other one. But there's no way just looking at a formula that you can determine, like if two things are soluble, which one is going to be a stronger electrolyte. You can't tell that just from the formula.
Would a magnesium bromide and sodium bromide be the same category?
Would they, or yeah, I always get confused on that one. Perhaps, yeah.
So which one would be stronger?
Oh, for that one question that asked you to rank them?
Yeah, that one.
I think they should be about the same. I think we played with that. Somebody else was.
Oh, I did that one time. I remember I did it. There was something I was thinking about when I did that. It was, oh, yeah, the one that forms more ions, I said was stronger.
Okay, yeah, that makes sense.
Because of one of them,
Yeah.
were balanced to form like a sodium bromide, you had to have two sodiums, so I said that was stronger because there were more ions.
Yes, that makes sense. So magnesium bromide forms more ions in solution per mole. So we might say that that's a stronger electrolyte.
How would we figure out?
What?
How would you figure that out?
Let's see. Is this the one? Yeah, magnesium bromide versus sodium bromide. So 1 mole of magnesium bromide forms 3 moles of ions in solution because it breaks apart into 3 different particles. And 1 mole of sodium bromide only breaks up into 2 moles of ions. So per mole, you've got more of the other. So that should be more conductive per mole. Whoa. Okay. No, you don't get to pick then. This is one that everybody got wrong. Let's see. Okay. Oh yeah, just disappeared for a second. Where'd it go? Cool. Oh, the definition of strong acid and weak acid. So you had a 50-50 shot now. All right, we went through that earlier, so that's all right. All right, what else? Anything else?
You know acid base, like when you get to the first part.
Yeah. Let's look at one of the ones in there. Butanoic acid, which is an organic acid, and is sometimes written in a different way, a slightly different way. Organic compounds are often written like this so that you see something about the connectivity. So the elements aren't grouped together, but they're kind of spread out so you can see how the parts are connected to each other. And the acid part is often written at the end as a COOH. We saw that earlier with acetic acid. So keeping that in mind and being told that this is butanoic acid, what would be the product of this reacting with calcium hydroxide. We'll say this is just pure by itself. Actually, that wouldn't be. Let's call that aqueous too. What do you think for this one?
So COOH is a compound by itself.
No, that whole thing is the compound, but the acidic hydrogen then is written at the end. So this is the hydrogen that would react with the base when you see it that way. Just like other acid-base reactions, you're going to form water. It's actually not, the organic compound doesn't break down further into CO2 like that, unlike carbonic acid. So you just write the rest of it. So you're going to have this would be this butanoate ion, and then you just put the calcium at the end of that. So it'd be 2 of those per calcium. Or you could put the calcium first if you like. I guess we've been doing it more that way, so let's do it that way to keep it consistent.
Can you one time go like kind of step by step how you figure that out?
Yeah. Did you have?
Yeah. How would you know the charge on lithium ion?
Okay, we'll look at both of those things. So one thing, we have to remember that acids in general have some number of hydrogens and then the rest of the part, whatever the other rest of the acid is. So if it's nitric acid, you've got 1 H and then NO3 is the rest of it. If it's sulfuric acid, you've got 2 hydrogens and then SO4 is the rest of it. In these big organic acids, it's really the same. The other part is just this big part. So if this is the acidic hydrogen, what we call the acidic hydrogen, that means that that's the thing that's going to be removed by the base. So the base is going to react with that part. That's the thing that's going to come off in solution as a hydrogen ion. And so the rest of it just kind of stays as it is. So if there's only 1 acidic hydrogen there, then you know that the resulting ion is going to be -1 because hydrogen ion is +1. So if there's one acidic hydrogen, then the whole rest of the chunk has to be -1 by itself. If there's 2 acidic hydrogens, then the chunk could be 2- by itself. We probably won't see that, but there are plenty of organic compounds with multiple acidic hydrogens, things like oxalic acid, which is often used as a cleaning compound. There's a bunch of other ones. there's flavor acids like malic acid and apples and things like that. But those would have multiple acidic hydrogens. So just look for those COOHs. I mean, this stuff, it won't come up on the exam, but you can look for those, and however many hydrogens you have to remove, that's how the charge of the resulting ion would change. We're generally going to see ones where there's just that one hydrogen. So this would be an example of a weak acid because it's not one of the ones in the list of strong acids. There's only a handful of strong acids. The rest are all, we call those weak. Does that answer your questions or just make it more confusing?
So would we encounter this in an exam? Yes.
You might see something like this in an exam. I would tell you it was an acid, and I would say here's and you could look for the acidic hydrogen, just like with acetic acid. But the rest of it is all just like any other acid-base reaction. You have hydroxide, and it combines with H+ and forms water, and then it's just a matter of putting the rest of the stuff together, the resulting things together.
Are you ever going to use like common names like glucose and fructose and stuff like that? And examples and all that?
No. Other than water, yeah, you should know that one. I'm trying to think if there's other ones that we use. The names of the ions and acetic acid. That's probably it. See you tomorrow. More? What else?
When did you say you specifically use N1, P1 plus?
When you're working out a dilution equation, when you're diluting something. So a problem might say something like, I'm just going to type this. How much of a 12 molar solution would you use to make 500 milliliters of 3.5 molar HCl? So in that case, you could set up an equation where your second two are the solution you want, the solution at the end that you're making. So that's going to be, actually, yeah, that would be 0.5 liters. That's your V2, and your concentration, your second concentration is 3.5 molar. And so initially you have a 12 molar stock solution, and you want to know how much of it to use. It's just making moles equivalent to moles. Volume times concentration gives you moles on both sides.
You only be given one kind of molarity, like HCl, you would be given like HCl and something else for these kind of questions.
Generally, yeah, right. You could, if you had multiple ones, you'd have to think about, you just have to do it separately. Like you'd need this much HCl and this much H2SO4.
There was a problem answering chemistry.
Was there one like that?
How do you separate it?
But
To get molarity of one, how do you separate it?
I don't know. It would depend how much information is given, I guess. Let's see if we can find that if there's one on there. Do you happen to know the number offhand? Limiting reactant. Which one is that? 4.111?
Yeah.
Oh, yeah, okay. So, right, this is the same idea. Let's look at these two things. there's the information, and then the question is here. So you've got a solution that has calcium chloride and magnesium nitrate in the solution. And then the question is, let me get that question. The question is, how much sodium phosphate would have to be added to 1.5 liters of the solution to completely eliminate the hard water ions? So you've got some magnesium and calcium ions in solution. You're adding phosphate to precipitate those ions out. I don't want to go through this whole problem because I think it's a good one and you should work on it, but I'll kind of show you how to get started with it. You've got these two concentrations. You can use that to figure out the concentration of calcium and the concentration of magnesium in solution, of magnesium ions. And then you have to kind of solve two different equations where those things react with sodium phosphate. So the two equations would be, oh, we got a purple line there all of a sudden, but you've got calcium chloride and sodium phosphate gives you calcium phosphate precipitate and sodium chloride. And so you have to balance that equation. And then you have to do the same thing with magnesium nitrate. Balance that equation. So then you use this concentration to figure out how many moles of calcium chloride you've got and how many moles of sodium phosphate you need, just a regular stoichiometry problem. Then you use this one for the magnesium nitrate, figure out how much sodium phosphate you need. And then you add up those two sodium phosphates to get your final answer because it says how much sodium phosphate would you need to get rid of all of those things. So you solve the two separately, and then you just add up those sodium phosphate amounts that you get at the end. Does that give you a sense of how to do it? In terms of dilution, if you wanted a solution that was this many molar in this and this many molar in this, and what would you start with? It's the same kind of thing. You need to have the same number of moles in both the beginning and the ending thing. So you don't think of the solution, the final solution, as being half this and half this. You think of the overall solution volume. You use the number of the overall solution volume for both parts because molarity is calculated versus liters of overall solution, not liters of solvent. So it doesn't matter what else is in there, the volume is still the volume. All right, what else do we got? Just stare at each other for 20 minutes. Maybe talk about some chemistry. Or we could just go. Feel good for the quiz tomorrow? Excited? Yeah. Chapter 4. I mean, know the names and things like that because that was from before, but it'll be equations, limiting reactants, balancing equations, solving for whatever. Yeah. It's a quiz, so it's not going to be comprehensive. There's just too much stuff in chapter 4, but it'll be a selection. That's chapter 3, I think. So we'll do that on the exam. Probably one question in the exam about that, I would imagine. I haven't finished writing it yet, so I'm not sure. All right. Should we call it a day? Study some more. All right. Well, let me know if you come up with more questions. Send me an email or something. And I'll see you tomorrow for the quiz.